This video will cover section 2.6 of Cal 1 concerning related rates. And so when we think about related rates, they involve, if you'll keep this in mind, how to relate a formula to its change according to time. Alright, so all the formulas we're going to look at are going to be looking at how is things changing according to time. At a certain point of time, what would be the volume? At a certain point in time, what would be area? What would be velocity? What would be the distance? And etc. It could go on. Alright, so it just depends on what the problem is asking. So when we think about solving related rates, sometimes we can use this acronym here to help keep us organized and make sure we have all the information we need. A lot of things you can draw a diagram, some type of picture to help you see what's going on in the problem. There's going to be some rate that's listed. Make sure you label it and decide what is that rate for. Then you're going to need to find an equation. So if we're talking about volume, you're going to need to find the equation for, or the formula for volume. It may be for a sphere, for a cylinder, a cone, whatever. We may talk about triangles, where you have to use Pythagorean theorem, things such as that. Alright, then once you find the equation, you're going to take the derivative of it, because the derivative is all about rates. Alright, and then there's going to be some information that they give us in the problem that after we take the derivative, we'll be able to substitute that information back in to solve for what they're asking us to solve for. Alright, now before we actually get into solving these word problems on unrelated rates, I just want to take a look at using the derivative, alright, on the formulas. Because remember, as we just stated, related rates is how that formula, how to relate its change to time. Okay, how to relate a formula to its change according to time. Now, we're going to just look at the formula for volume of a cone, and I want to show you how, if I'm wanting to know how they change according to time, I'm going to have to take the derivative with respect to time, but notice there's no t variable in my formula. So I just want to work through the formula and let you see what the derivative looks like, and then we'll go back and actually do some examples that are a little less complicated maybe. Alright, so if I have the volume of a cone, that formula is volume equals pi over 3 times r squared h. Alright, and there's no t in there. The formula is not solved for t. Alright, but I need to find the values of each variable. Alright, and those variables are v, the volume, r, the radius, and h, the height, with respect to t or time. Alright, to do that, this is where implicit differentiation is going to come into play. Alright, because all of these variables, their values are going to vary based upon some specified time. At what time is the water level this in my cone, or at what time or is the height of my cone this, or at what time is the ladder a certain distance from the wall, things such as that. Alright, so I want to look at the formula, alright, and just see what it's going to look like when I differentiate it. So remember, to differentiate, you take the derivative of both sides, and this time we're going to derive it with respect to t. So I'm going to take the derivative with respect to t of the left side of my formula, so that's v. Then I'm going to take the derivative of the right side of my formula, so that would be pi over 3 r squared h. Alright, and then what I can do is when I take the derivative of v with respect to t, remember how we did with implicit differentiation? If this is not the same as this, then my derivative would be 1 times the derivative of v with respect to t. So remember how we did it in section 2.5. If I were taking the derivative with respect to x of y, it was dy over dx. Alright, now I'm taking the derivative of v with respect to t. These two things don't match up, so I have to take the derivative of v with respect to t. Alright, on the right side, I'm going to pull out that pi over 3. and then take the derivative of the inner part there. Alright, so I'm going to take the derivative of r squared h. I'm going to go ahead and put it in parentheses so maybe you can see what I'm doing. This is a product, so I would say, you can do it either way here. So I'm going to say r squared times the derivative of h. So that would be 1 times the derivative of h with respect to t, plus h times 2r, derivative of r squared, derivative of r with respect to t. Alright, so I just used the product rule here. I did first times derivative of the second plus second times derivative of the first. When I took the derivative of r with respect to t, I had to do dr over t. And when I took the derivative of h with respect to t, I had to do dh over dt. Alright, because that bottom doesn't match the variable that I'm taking the derivative of. Alright, then if I just kind of do a little simplifying here, I can say that the derivative of v with respect to t would be pi over 3 times r squared dh dt, and then I can kind of put those two r and h's together, 2rh dr dt. Alright, so that's going to be the derivative of my formula for the volume of a cone. Now in the problem, they're going to give you some rates. Alright, they may give you the radius of the cone, they may give you the height of the cone, they may give you something to do with the way the radius is increasing or decreasing, or it may have to do with height. So you're going to be filling in for something and solving for one of the variables. So I may be solving for v, I may be solving for r, or I may be solving for h. I just have to look and see what the problem is giving me. But I wanted you to see, alright, taking the derivative of the formula implicitly, how we have to do the dv dt, dh dt, dr dt, where that comes from. Okay, so let's take a look at a specific example here. Alright, so I want to look at the radius r of a circle is increasing at a rate of 4 centimeters per minute. Alright, and then I want to find the rates of change of the area. Alright, for two different radiuses. One when the radius is 8 centimeters and one when the radius is 32 centimeters. So I'm just going to look through the problem and see what information I do and don't have. Alright, so if I'm thinking about drawing a diagram, we're talking about circles here. Alright, and remember the radius is the distance from the center of the circle to the outer edge of the circle. Alright, so this is my r right here, and it's going to be increasing, so my radius, meaning the outer edge of my circle, is going to be increasing. Alright, so it'll just continue to increase. Alright, at 4 centimeters per minute. Alright, so let's just get that part in our head. Alright, then if I think about the rate, it says the radius is increasing at a rate. Looking for that word rate of 4 centimeters. So if I'm thinking about circles, alright, then it asks me to find the rate of change of the area. So we're talking about the area of a circle. So if I'm looking at equations, if I think about the equation I'm going to need, alright, that would be the area of a circle, which remember area of a circle is pi times the radius squared. Alright, now what I want to do is take the derivative here. So I want to say the derivative with respect to time of a equals the derivative with respect to time of pi r squared. Alright, when I take the derivative of a with respect to t, alright, that would be 1 times dA dt. And then when I take the derivative of r squared with respect to t, I'll get 2 pi r. So I'll bring that 2 down, subtract 1, dr dt. Alright, so here's the what I'm going to need. Alright, I got to figure out what do I have and what am I going to solve for. Alright, so what it has told me is that I have the rate of my radius. That's going to be my dr dt. The rate that my radius is increasing is 4 centimeters per minute. So I know dr dt. Alright, so I could say the derivative with respect to of a with respect to t would be 2 times pi times r times 4. Alright, now in my problem, they're giving me r. So for a, alright, a, let me get down here where you can see what a is. A, for part A, I want the radius to be 8. So I'm going to come, and in place of r, I'm going to fill in an 8. So that says the derivative of a, or the area, with respect to t, would be 2 times 4 is 8, times 8 is 64 pi centimeter squared per minute. Alright, then part B, alright, asked me to find the rate of change of the area. That's this right here, the rate of change of the area with respect to time when the radius is 32 centimeters. So I'm going to use this same formula here, fill in my information. So the derivative of the area with respect to time is 2 times pi. Alright, and we said r is 32, and we said dr dt is 4. Alright, so when I multiply that out, I'll have dA dt equals 4 times 2 is 8, times 32 would be 256 pi centimeters squared per minute. Now remember, it's centimeters squared because we're talking about area, so when I square the radius, I should get centimeters squared. So as you can see what I did there, 256 pi centimeters squared per minute.